Hello, and welcome back to the Calculus 1 playlist. In today, we're going to be talking about some common functions and transformations, and we'll do a couple examples relating to them. So without further ado, let's begin. So, common functions. So to start, we'll start with the most basic type of function. We have a linear function. So a linear function is just a function that follows this rule. F of x is equal to mx plus b, where m is the slope and b is the y-intercept. So an example of that, if we draw a graph, would be this line. Y is equal to x is a linear function whereby m is equal to 1 and b is equal to 0. So fairly straightforward. We've all seen linear functions before. The next type of function is the polynomial. Spelled that wrong. So a polynomial function would be defined as f of x is equal to, and I'll write this out then explain it, n x to the n plus a n minus 1 x to the n minus 1 plus, and we keep going, a2x squared plus a1x plus ao. Great. So this function right here, this is a polynomial function, and you should also define it like this, such n is greater than 0. Positive integers. So this is the common, I guess, term for a polynomial function. So we have n being the coefficient, or an being the coefficient, with n being the degree. So degree, coefficient, and your x variable is your independent variable for that function. So again, we've seen these types of functions before. I'll give you an example of one. F of x is equal to 3x cubed plus 2x squared plus 5x minus 2. That is an example of a polynomial function. So fairly straightforward. So the next function we're going to touch on is a rational function. A rational function is just the ratio of two polynomials. So let's write that down. Again, very straightforward. So we could say f of x is equal to 3x cubed minus 14x squared plus 2 all over x to the 2 minus 3x plus 4. So that's a simple rational function for you. It's just the ratio of two polynomials. Again, this is a polynomial, and this is a polynomial. So very straightforward. So the next function is a power function, and that has different subsets. Power function. Now the power function is just defined as the following. F of x is equal to x raised to a. And in this case, a being greater than 0. Great. And more specifically, positive integers. Great. So an example would be f of x is equal to x cubed. In this case, a is equal to 3. This is the definition of a power function. So it's just a function who's raised to a specific power. Great. So one of the subsets of a power function is known as the root function. Root function. Now in this case, the root function, this a value, and I'll make this more clear, that's an a is equal to 1 over n, where n is greater than 0 or some positive integer. So in this case, to give you an example, you'd have f of x is equal to x raised to 1 over 2. This is the definition of a root function, and we know that this is equal to the square root of x. Another one being f of x is equal to x raised to 1 over 3. That's equal to the cube root of x. Really straightforward. Another example of a power function is a reciprocal function. So the reciprocal function in this case is defined when a is less than 0. So pretty straightforward. Again, I'll give you an example. F of x is equal to x negative 1. So we know that that's equal to the reciprocal of x, which is 1 over x. If we had f of x is equal to x to negative 2, we know that that's 1 over x squared. So very straightforward. And I'll clarify for this, negative numbers. If we have a combination of a root function and reciprocal function, it's kind of just known as a power function. There's no definition for it, but I'll give you an example of that. Let's say f of x is equal to, let's do x raised to negative, and we'll do negative 1 over 2. This is equal to 1 over x. And you can kind of work that out, but that's as such. Great. And the last type of function, and probably one of the more important ones to remember its properties, is the trigonometric functions. So a trigonometric function is any function containing cos, sine, tan, along with reciprocals. Great, really straightforward. So let's do a quick review of these trigonometric values. So this is a right triangle. I'm going to connect it right here, 90-degree angle. So we have side A, B, and C. And if you recall, for sine, cos, and tan, and let's call this angle theta, 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 theta. This is equal to B over C. This is equal to A over C. And this is equal to B over A. Great, so you're just observing the side lengths and creating relations to each angle. And for the reciprocal functions, so for sine, we have cosecant theta, sec theta for cos, and cotangent theta for tan. So this is equal to 1 over sine theta, which is equal to C over B. This is equal to 1 over cos theta, which is equal to C over A. And this is equal to 1 over tan theta, which is equal to A over B. Perfect. So let's look at a quick example of working with functions, and this will kind of tie into our previous discussion of domain and range, be a fairly straightforward example. And before then, actually, I want to talk about a little bit more about these functions, the cos and sine theta. So if you recall from your high school discussion, and I'm going to use 2 graphs to demonstrate something. Okay. Let's say we have a value of, right here, this theta is equal to pi over 3. Equivalently, we could say that pi over 3 is equal to 2 pi plus pi over 3 in terms of their angle values, right? So what do I mean by that? In this case, we'd go back like this, and you'd have 2 pi plus pi over 3. So when we're describing our angles in our coordinate system, one entire revolution around our coordinate system is exactly 2 pi, or 360 degrees in degree mode. So when we're computing these different angles, we have to recall that integer values of 2 pi, or as I call it, 2 pi n, where n is an element of the integer system. This is the symbol for integers. For any integers, whether positive or negative, that will get us back to the exact same position. So that's something that will be important for this next example. Great. So let's go through and solve a worked example, kind of using this in mind as well. So example. What is the domain of the function f of x is equal to 1 minus 2 sine of x? Great. Solution. So to solve this equation, we know that, or to find the domain, we know that the denominator can never be 0, and that is the only restriction on this type of function. So let's find where the denominator is 0. So we set the denominator y minus, or 1 minus 2 sine of x is equal to 0. Now let's solve for sine of x, not necessarily x, but let's solve for sine of x. We go sine of x is equal to 1 over 2 if we subtract 1 and divide by negative 2, we get that sine of x is equal to 1/2. Great. We know intuitively from the unit circle, if you recall, that the solution to sine of x is equal to 1/2 happens when x is equal to pi over 6 as well as 5 pi over 6. This is just from the cast rule. Which tells us which is what values of an angle are positive and negative for the different trig functions. So for the trig function of sine, we know that the values in the first and second quadrant, so this quadrant and that quadrant, will be positive, and in this quadrant and this quadrant will be negative. Thereby, we can say that pi over 6 right here, as well as 5 pi over 6 equal to 1/2, whereas their counterparts in these two quadrants would be negative 1/2, which is great. That's just a quick review of that. If you don't recall, you might need to remember some of your trigonometric rules and such. It's okay. It's not too difficult of a concept to grasp, but you should go ahead and review that. But we know that solving the equation sine of x is equal to 1/2 returns the values of x is equal to pi over 6 and 5 pi over 6. And recall, we stated here that any integer value of added on of 2 pi will give us back to the same point. So we need to exclude pi over 6, 5 pi over 6, as well as any integer value or any integer value multiplication of 2 pi to that adds on to these values. So what do I mean by that? So x is equal to pi over 6 plus 2 pi n, as well as 5 pi over 6 plus 2 pi n. So 2 pi multiplied by n, where n is an element of the integers, positive and negative. Sorry, that's a terrible sign. Let's do it like this. Dun. Where n is an element of the integer system, then we would have our solution. So we can say our domain, then, since these are the points not included in the domain, since they make this expression 0. So we can say x is an element, x is an element of the real number system where x does not equal to pi over 6 plus 2 pi n, as well as 5 pi over 6 plus 2 pi n, where n is an element of integer system. And we can put these in curly brackets to know that this is our set of all solutions. So we kind of read this as x can be an element of all real numbers except when x is equal to this value or this value. And our values of n are just all the real integers. Great, so let's box this as this is our solution. Perfect. Okay, so let's talk about transformations. And to do so, I'm going to need a couple graphs. Put one here. Let's put one here. Great. So the first type of function transformation we can do to graphs is a translation. So a translation is just a type of function transformation in which we move a function either up or down, left or right, on I guess in reference to the coordinate system. So let's say we have x, y, and this is f of x. So I'll write down the transformations or the translations, and then we can go through them afterwards. So we have y is equal to f of x plus c. Y is equal to f of x minus c. We also have y is equal to f of x plus c inside the f of x, and y is equal to f of x minus c. Now let's look at these translations. So the first one where we have, or the first two that I wrote down where we added c and subtracted c are vertical translations. So they will translate the function up or down. So for the first one, we'd had y is equal to f of x plus c. Then we go like this. So this being y is equal to f of x. This is y is equal to f of x plus c, where we translated a distance of c. Every point gets shifted a distance of c. Conversely, for f of x minus c, we would get y is equal to f of x minus c. So the function should remain exactly the same. It'll have the exact same shape, except now all the points are translated up or down by a specific value, the constant of c. For the left or right motion, we have f of x plus c and f of x minus c. This one can be a little bit tricky, but just remember that if we have f of x plus c within the f of x, we're moving to the left, and f of x minus c, we're moving to the right. So in this case, if we go this way, we'll go this is y is equal to f of x minus c because we move to the right. I'm going to give us a little bit more space. That. And then if we're going to translate this way, we would have y is equal to f of x plus c. And that's this coming this way. Great. So those are the translations, and the last two that I want to talk about are stretches and reflections. So looking here, let's again draw up our line. Let's call this y is equal to f of x. So if we want to stretch, we would have two types of, I guess, transformations. Y is equal to c f of x, or y is equal to 1 over c f of x. So the one where we multiply by the value of c, we're kind of elongating or stretching our function value. So let's do that. This would be like this. As you can see that it's kind of exaggerating the endpoint conditions, but we have y is equal to c f of x. And for the other one, where we're taking the inverse of 1 over c, so we're kind of making it smaller, where c, in this case, write that down, c is greater than 0. If we're taking 1 over c times f of x, then we're kind of shrinking f of x. So that becomes like that. Y is equal to 1 over c f of x. And last but not least, we have the reflection. So to reflect about the y-axis, so if you want to say this is the y, this is the x, if we want to reflect this function about the y-axis, what we would do is we would use y is equal to f of negative x. So that would be just a reflection about the y-axis. Oops, let's take away the arrow. So we're kind of just reflecting across the y-axis, as you can see. So this is y is equal to f of negative x. To reflect about the x-axis right here, we would just go as such. Let's draw it out. That is y is equal to negative f of x. So y is equal to negative f of x to reflect about the x-axis. Great, so it's not too terrible. There's just some rules to remember when you do this, but overall it is fairly straightforward, and we're going to go through an example where we take a function and we describe its transformation and then graph it. Great. So example, y is equal to root 2 minus x minus 3. Describe transformations from root x onwards and graph the function. Perfect. So let's graph y is equal to root x first. We know that y is equal to root x is kind of the following. Y is equal to root x. So how do we do this? So to start, we're going to have, let's go like this, f of x is equal to root x. The first transformation that we do is we reflect about the x or about the y-axis. So reflect about y-axis. This gives us f of x is equal to root negative of x. That's how we get the negative symbol. And as you remember, that's across the y-axis, so that would come like this. Y is equal to root negative of x. Then we need to translate. And to incorporate this 2 minus x into the term, we're going to translate the function either left or right. And to do so, let's go as such, let's plug in. So it becomes negative. And when we plug into x, let's plug into x minus 2. Because if we do that, we see that we get root 2 minus x. And so if we're plugging in x minus 2 here, we're translating our function 2 to the right. So that becomes 1, 2 units. Let's call it right there. Like this, and the green, y is equal to 2 minus x. So let's say translate 2 units right. Then we translate 3 units down to incorporate this term. So that becomes f of x is equal to 2 minus x minus 3. And this comes down here. Let's use gold. And our function kind of looks like this. Y is equal to 2 minus x minus 3. This is our final solution. Let's just put y, x. Great. So not too bad. Overall, we kind of talked again about the common functions that we have. So linear functions, what they look like, polynomial functions, rational functions, power functions, and specifically the root and reciprocal functions, trigonometric functions, and we introduced transformations by translating, stretching, and reflecting different functions. Great. So if you enjoyed today's video, please feel free to leave a like, comment, subscribe, and I'll see you in the next video. We'll be talking about compositions. Thank you.